Hello. In this section, we're going to be looking at three-dimensional shapes. Yesterday, we were looking at the two-dimensional figures. So have your note packet out to 1.7. If we don't all have it out, maybe pause the video until everyone's ready to go, but I'm going to assume we are ready. The very first word in this section is polyhedron. This is the three-dimensional version of the word we learned yesterday, polygon. A polyhedron is a solid with a flat surface that encloses a single region of space. There are three other words associated with a polyhedron. There is a face. Face are all the sides of the figure. The vertex is any point, and an edge is the line segment that connects one face to another. There are two types of polyhedrons. There are what we call prisms. A prism is when we have two parallel congruent meaning equal faces, called bases, connected by parallelogram faces. So it's a polyhedron in which the top and bottom match each other. So the big difference is, if you imagine the polyhedron is a loaf of bread, if you made parallel cuts, like slicing the loaf of bread, each cut would have the exact same size. Unlike what we call a pyramid. A pyramid is when we have a base and they meet all together at a vertex. It's when we have a polygonal base and they meet at the top, the vertex. The difference here is if you made cuts of this loaf of bread, cutting parallel to the base, as you cut, moving from the bottom to the top, your pieces are going to get smaller and smaller. They change as you move up and up and up. So we have unequal cross sections for a pyramid. We have equal cross sections for a prism. Examples of things that are not polyhedrons: essentially anything that has a curved surface. A cylinder is not a polyhedron. A cone a cylinder is a figure where we have a circular base. So it's a circular prism, really. A cone is a circular pyramid, but because of the curve, it is not a polyhedron. And a sphere is the three-dimensional version of a circle, the set of all points that are equidistant from the center. When we name a polyhedron, we name it based on whether it's a prism or a pyramid and its base. So in this case, the base is a triangle and it's a prism, so we say triangular prism. Here, the base is a rectangle and it's a prism, so we'd say rectangular prism. Here, the base is five-sided, so we'd say it's a pentagon, and it's a prism. The top and bottom are the same shape. So pentagonal prism. All of these meet at the top, so there's a vertex. So these are all pyramids. The base here is triangular, so we'd say triangular pyramid. The base here is a rectangle, so we'd say rectangular pyramid. And the base here is a pentagon, so we would say pentagonal pyramid. That's how we name polyhedrons, based on its base and whether it's a pyramid or a prism. Example, we're going to try it for ourselves. State whether each is a polyhedron. If so, identify and name the bases, faces, edges, and vertices. The first one is not a polyhedron. It is a curved surface. We call it a cone. Second one, this is definitely a polyhedron. It is a triangular, because the base is a triangle, and it's a pyramid, so we'd say, not triangle, say triangular pyramid. Once we know that, it asks us to name the bases, faces, edges, and vertices. I'm going to zoom this so it makes it a little easier to see. The bases, it has one base. It's triangle ABC. There are four faces, so you'll notice if you are a base, you are automatically a face. The face is triangle ABC. That's the bottom. The left triangle, ADC. The right triangle, CDB. And then the back triangle, BDA. There are, six edges? There are three along the sides and three down below. AB, BC, CA, DA, DB, and DC. There are four vertices. There are three down below and the one up top. So there will be a couple questions that ask you to name things like this. How many bases, how many faces, how many edges, how many vertices? You name the faces based on the shape, and you name the edges based on the line segment, and the vertices based on the point. I'm going to give you a chance to try. State whether each is a polyhedron. If so, identify it. Then just name, don't actually list them all out. Let's just do this. Let's just say state the number of bases, faces, edges, and vertices. You don't actually need to name them. That would take a while for whichever figure. So pause the video now. Give people maybe 2 minutes to try this question and come back after everyone's had a chance to try. Here we go. Let's do the one on the right first. That is a cylinder, not a polyhedron. This one on the left is a polyhedron. It is a rectangular prism. The base is a rectangle and it is a prism, so we would say rectangular prism. There are two bases, the top and bottom. There are 6 faces, the 4 sides and then the top and the bottom. There are 12 edges. There are 4 edges up top, 4 edges on the side, 4 edges down below. There are 8 vertices. There are 4 points up top and 4 points down below. Last kind of vocab word for the day is what we call a regular polyhedron. This is the 3-dimensional version of a regular polygon. A regular polyhedron is a polyhedron whose faces are all regular congruent polygons. Plato, a Greek mathematician, was the first person to discover that actually in our 3-dimensional universe there are only 5 possible, and because he was the first to discover them, we call them the Platonic solids. The first one is a tetrahedron. It's the 3-dimensional figure we get from 4 equilateral triangles. Then we get the cube, 6 square faces. We get what's called the octahedron. That's when we have 8 equilateral triangular faces. We get what's called the dodecahedron, do meaning 2, deca meaning 10. It's a 12-sided figure where each side is a regular pentagon. And then we get the icosahedron, which is a 20-sided figure. Each side is an equilateral triangle. Those are the only ones that are possible. And these are usually, if you play a lot of board games, you might recognize these. These are some common dice figures because they're the only Platonic solids. A little side history about Plato and the school that he developed. The school in Athens, Greece that he developed was called the Academy. It was established in 387 BC. It was the building and gathering spot just outside the walls of Athens in Greece. It was named after the local hero whose shrine was nearby. The academy was not necessarily a school or college in the modern sense, but rather it was more of a gathering and informal association of people who were interested in studying philosophy and math and astronomy at the time, and Plato was their guide. The academy became so famous it was the gathering place for intellectuals, and it continued to operate for 900 years after Plato's death, with periods in which it was directed by a number of distinguished philosophers. Aristotle was a student of the academy. A famous story about the academy, above the entrance to it hung a sign. That sign in Greek said, "Let no one ignorant of geometry enter." So a little aside about the history of geometry. Similar to yesterday for 2D figures we studied the perimeter and the area. For 3-dimensional figures we study the surface area and the volume. The surface area is the measure of the amount of area it would take to cover the outside of that solid. It's the sum of the areas of all of the faces, and the volume is a measure of how much space each figure would occupy. I would highly recommend writing these formulas down wherever you would do the homework for this section. If you need a little bit more time or you want to see it later, it's on page 69 of your book, but I'm going to scroll down so that you can see it, and then I would recommend maybe pausing the video now for 2 minutes to give people a chance to pull out wherever they would do the homework for this section and write down the 10 formulas, 2 for each of the 5 shapes for each figure that occurs in this section. So pause the video now, give people a couple minutes to write down the formulas, and then unpause it once people are ready. Hopefully you got the formulas down. We're going to use a few of them here in a moment. One thing I want to mention, a number one common mistake I see people make almost always has to deal with the cone, and they confuse the height with the slant height. If you noticed, they told you what the variable stood for in each equation. L stands for slant height, R stands for radius when you're dealing with the cone. The slant height is used for the surface area because the slant height is along the side, and that's the area. The height, the actual distance from the vertex to the center of the base, that is used for the volume. So the actual height of the cylinder is used in the volume. The slant height L is used in the surface area calculation. So make sure you note that. Similar thing happens with the pyramid. Okay, example. Find the volume and surface area for the Great Pyramid. Yeah, that's in Egypt. Volume first. Volume for a pyramid, if you go back and consult, volume of a pyramid is 1/3 big B times H. Big B is the area of the base. The base is a square. So I need to do 1/3 times the area of the base is 750 squared times the height of the pyramid. The height for volume is the distance from the center of the base to the vertex, which is 455. Grab a calculator, I'm going to multiply all this out. 1/3 times 750 squared times 455. And I get 853.12500. My units in this case are feet cubed. Volume is measured in cubic units because there are 3 dimensions: length, width, and height. Now I'm going to find the surface area. Surface area for a pyramid. I go back here, surface area is 1/2 big P, which is the perimeter of the base, times L, which is the slant height from the vertex down to the side, plus big B, which is area of the base again. So surface area, 1/2 P times slant height plus B. 1/2 P is the perimeter of the base. Well, that's 750 times 4. That's 3,000. L is the slant height. Essentially what you're doing is you're finding all of the sides in this piece. This piece right here is the sides, and this piece right here is the area of the base, and that's the total surface area. Well, all the sides are triangles. 1/2 the base is, and then the heights, which is the slant height. So 590 plus the area of the base. The base is a square, 750 by 750, 750 squared. Then I grab a calculator and I run it. 1,500 times 590 plus 750 squared. I get 1447500, and my units on this are feet squared since it's surface area. And that is how we can calculate volume and surface area for a pyramid. To give a little bit of perspective, I mean, this is 85 million cubic feet. A cubic foot is a foot by foot by foot. 85 million of those. Here's a picture for reference. Here's standing from the bottom looking up. That looks like it almost reaches all the way to the sky and goes on forever. This is a person right here. Each block is about as tall as the person, so you can see how many of these blocks it takes to make the Great Pyramid. It is huge. It is, yeah, very, very large. Okay, I'm going to give you a chance to try. For yours, I'm going to ask you for dimensions from a cylinder. So calculating volume and part of a surface area. First question, how many gallons can this pool hold? It's a volume question about the cylinder. And how many square feet of liner would it take to make the pool? Just the side and one bottom. So you have to adjust the formula a little bit that you were given, because I do not want the top, because I want to be able to get into the pool. So pause the video now. Give people maybe 2 or 3 minutes to try. Also note, I want to know gallons, so you'll need to find cubic feet and then multiply by 7.5. And unpause the video once everyone's had a chance to try. Okay, here's the first one. First one, volume. Volume for a cylinder is pi r squared times h. Pi, the radius is 4, so I'll square that times 3. That will give me cubic feet, and then to get from cubic feet to gallons, I need to multiply by 7.5, because that's how many gallons are in 1 foot. Over here to do the surface area, the surface area is, here's the side, 2 pi rh, and then I just need the bottom. I don't need 2 because there is no top. So I run it with r is 4, the height is 3, and I end up with 125.66 square feet of liner is what I should have got. So that is it. As you're working on the homework, answers for this section are right here. If you would like to leave the video paused and the answers up there as you work, feel free. Otherwise, thank you very much and have a good day.